Okay, well, we're going to get started. This is our last colloquium talk for this semester, so welcome, especially on a potential snowy evening. We have Dr. Alexis Byers, who was Lexi while she was a student here. So, and she's going to talk with us about graph theory and a colorful introduction to graph theory. But she grew up in Northeast Ohio, near Cleveland, and then came to Wittenberg for math. Got her Bachelor of Science degree in math in 2014, and while she was here, she took her first graph theory course from Dr. Higgins, who is teaching graph theory again this semester, and she's been working in graph theory ever since. Must have had a good impact. Right. After Wittenberg, she went to Western Michigan University in Kalamazoo, Michigan, and got her PhD in math, which graduated in 2018, right? And then went and accepted a job teaching as an assistant professor of math at Youngstown State University, which is where she's been. It's her second year teaching, currently teaching Honors Calc 1 and a research graph theory course kind of for seven students?
Yes,
seven students in graph theory, which is kind of cool. So she's going to introduce us to graph theory and kind of talk about some research that she's doing. So let's give her a welcome.
Okay, thank you so much. So thanks for coming and thanks for having me. This is a little nerve-wracking because I know people in the audience. I feel like it's less nerve-wracking when I know nobody. So be nice to me. So first I want to give a little bit of acknowledgement to the impact WIT had. So I came to Wittenberg. So when I was applying, there's some good pictures. So I originally wanted to be an English major when I applied to go to Wittenberg. And I changed my senior year to math because of a superficial reason. I thought I could get a better job. I thought I'd make more money if I was in math than in English, so that's really why I chose it. And I had no idea what I wanted to do. I only had calculus, obviously, before I came here. And so it turned out, I found out that I really liked pure math. I took, intro to proofs with Dr. Higgins. Dr. Parker encouraged me that I could go to grad school. And it was Dr. Higgins' graph theory class that kind of led me to pick a track for that. I remember Dr. Parker asked me what would you want to do in grad school? And I was like, I don't know, everything's fine. I like everything well enough, but nothing's jumping out at me. And then I had the graph theory class, so that's what I chose. So we were able to go to conferences like the local MAA meeting. So here's the first one. Yeah, Dr. Higgins is there, Al, Dr. Parker, and Dr. Shelburne are in that one, right? Yeah, so there's a couple more at the end. So. And also I got to do an REU that Dr. Parker kind of advised me that I should do. So I did research in graph theory for the first time that summer, the summer before I graduated at Miami University. And then I did an honors thesis with Dr. Higgins in graph theory, and then I applied for grad school in graph theory. So so there's a little bit of life after WIT, but so I went to Western Michigan University and worked under Ping Zhang. So I specifically went there for graph theory because she was kind of the guru in graph theory at Western Michigan. So I did my dissertation in graph theory on, among other things, graceful labelings and coloring. So that's kind of what we're going to talk about today. I feel like that's a good way to kind of introduce graph theory. Is through colorings and labelings and fun stuff. And now I'm a professor at YSU, so it's kind of full circle. I taught an intro graph theory class last semester, kind of like Dr. Higgins did for me, so that's been really fun. And now I have my own graph theory students, so it's been really cool. This picture is from going to another conference, so that's kind of part of one of my favorite parts about being a mathematician is going to travel and conferences and stuff. So this one was in Florida in March, right? So actually I can wear a skirt and no jacket, and it's really nice. So another reason to do math, right? Okay, so motivation for this talk. First, I'm going to have two kind of different problems that I want to talk about, and then at the end there's a concept that kind of combines the two. And as a sub-theme, this is kind of just asking the right question, which is kind of a big thing in research, right? So if you kind of ask the right question, put things together in the right way, you can come up with something really interesting. And then also, hopefully to show you the graph theory is cool. Hopefully, Dr. Higgins has shown you that if you're in his class. But and it's a really great area to do research, right? So there's a lot of open questions and a lot of just asking the right question and being able to do kind of original research. So, all right, so getting on to actual math stuff. So this quote, I really like this quote, so I'll start off with that. We'll come back to the end and hopefully it'll make a little bit more more sense, but this was by William Tutt said this in the Journal of Graph Theory after some huge breakthrough in graph theory. So, right, so this part starts in 1852 with Francis Guthrie, who was looking at a map of England and could notice that he could always color it with 4 colors, so that any two regions, any two counties that had a common boundary were colored the same. And so we kind of wondered, is this always true? And so it eventually led to a really famous problem, which probably some of you know, which is called the 4-color problem. So we asked, can all the regions of every map, whether or not it's real or imaginary, no matter what you choose, can it always be colored with 4 colors or fewer, so that regions that have a boundary don't have the same color? All right, so here's an imaginary map from Lord of the Rings, one of the movies that me and my grad school friends watched while we were in grad school. So you can actually color this map with 4 colors. And you actually can't use any less than 4 colors, right? So when we ask this kind of question, we should ask whether or not it can be improved. But for this guy, it cannot be improved specifically because of what's going on over here. So if you see this Rohan and the region surrounding Rohan, you'll see that like these guys can't be colored in less than 3, right? And they're all surrounding him, so he has to have a 4th color. So we can't do any better. Here's a real map. So this is a map of like the southwestern United States. And so this one also you can color in 4 colors, but again, you can't do it in any better because of the situation where we have 5 going around, and if you think about it long enough, you can probably convince yourself I can't use less than 3 colors around here, so then we need that 4th color for Nevada. Okay? Alright, yes?
And when you say adjacent, then when you get the so-called 4 colors,
oh, yes.
Okay,
we're not going to count that, yeah. So it has to be kind of like, yeah, by a significant boundary, not just a point.
Got it.
That's a good question. Good. Okay, so as expected, right, this isn't a map talk, this is a graph theory talk. So we're going to turn these maps into graphs, okay? So if we take the map and we put a vertex in every single state, and then we're going to draw an edge between the vertices if they share a boundary, okay? So that original map is going to turn into this graph, okay? So the vertices are just these little points, and the edges are just ones connecting them. All right, so if we have this coloring of the map, we can easily make that into coloring of the vertices of the graph. All right, and again, you'll see that like, if we color this vertex pink, none of its neighbors are going to be colored the same color, right? Just like none of the regions over here that share a boundary have the same color. All right, so a couple different vocabulary words that I'll use a bunch. So order just means like the number of vertices, and size is just the number of edges. So this guy has order 6 and size 10. The degree is just how many vertices are incident with the vertex, or sorry, how many edges are incident with the vertex. So this guy would have degree 5, that guy has degree 3, and we'll use that notation, degree of B. The maximum degree is just the biggest degree, right? So this guy, the 5 is the biggest degree, so its maximum degree, which we're just going to call capital delta, is 5. Connected, right? So a graph is connected just if you can get from any vertex to any other by a path, right? So here's some examples of connected graphs that you'll probably see. So we have this path, right? Just kind of a straight line. We call that P4. This is 4 vertices. A cycle on 5 vertices is just C5, so it's just going around in a circle. This is a star, so we have one central guy connected to these 3 coming off of it, so we call it K13. And here's like, if you think about this as being one whole graph, that would be disconnected, right? With 2 different components, because I can't get from like that vertex to over to that vertex. The most popular types of colorings are proper vertex colorings, right? So we saw an example of what a vertex color would be, just coloring vertices. But the most popular is actually what's called proper. So this is just a fancy way of saying, right, we color the vertices, and 2 vertices that share an edge aren't going to be colored the same. That's it. Okay? So that's a proper vertex coloring. Here's 2 examples of a proper vertex coloring of this graph. So the one on the left is just like you pick a different color for every vertex, right? That's always going to work. But if you're a little bit more clever, we can make these vertices have the same color because they don't share an edge, right? So in general, the more interesting question is what's the fewest number of colors we can get away with, right? Because I can always just give a color to everything and that's going to work. So the chromatic number is this minimum number of colors that we need, and so we call that chi-G. All right. So we have some bounds for the proper vertex coloring. In general, this is a hard thing to determine, but we do know that it can't be bigger than delta plus 1, and it's only going to achieve that bound if it's a complete graph or non-cycle. Right, so we can do the same thing for edges. We can color edges if we want to. And again, a proper edge coloring is just going to be coloring the edges so that two edges that are adjacent to each other don't have the same color. Okay, so again, the same graph, now edge color. So on the left, again, we can give every edge a different color and it's always going to work, right? But we can do a little bit better here. These guys don't touch each other, those guys don't touch each other, so we can get away with 3. So in general, we want the minimum number, right? So that's the chromatic index of a graph, chi prime, right? And actually we know exactly really what this is going to be. It's going to be one of 2 cases. It's going to be exactly the maximum degree or exactly the maximum degree plus 1. Oops. All right, so a lot of mathematicians believe that this 4-color problem was true, and so it turned into a conjecture. And in graph theory terms that we just learned, the 4-color conjecture is just that every planar graph, so planar just means that you can draw it in the plane without edges crossing, right? Because that's just a direct connection to this being a map. So every planar graph has chromatic number at most 4, right? So we'll never need more than 4 colors to properly vertex color the graph. All right, so it seems pretty simple, just coloring vertices, right? And the idea is simple and easily stated, and you could give it to, you know, a 5-year-old and they can color vertices and come up with things. But it's not an easy question to answer, right? So it took 124 years to answer it, and some people still aren't quite satisfied with the proof, right? So I'm going to talk a little bit about that process. So for 124 years, no one could provide an adequate proof that you didn't need more than 4 colors, and also no one was able to find a counterexample, right, that needed more than 4 colors. So an interesting part of this that I'll talk about, just because I find it really interesting, is that for 11 years they didn't think it was solved by someone named Alfred Kemp, right? So at the time he was an amateur mathematician, and he was actually a student of Arthur Cayley. And so he had claimed that he had solved this problem in 1879. And so his advisor told him he should publish this. And so he published his proof in the American Journal of Mathematics. And so he got a lot of praise. He was even elected as a fellow of the Royal Society for all his work that he did. So the basic idea, which is really a really clever proof, is he used these things called Kemp chains, which I won't get into detail about, but basically they're just chains and loops, and you can switch colors on and off, and you can prove that you don't need more than 4 colors in these little Kemp chains, just being able to switch it up. So he went into great detail about the case when you have 1 region surrounded by 4 regions, right? And that case is true, but he just kind of claimed that the similar thing is going to work in the case when you have 1 region surrounded by 5. And so that was kind of his downfall. That wasn't quite true. And so Percy Haywood published a paper and pointed out this error and came up with a graph such that we had one vertex surrounded by 5 other, and you couldn't do this Kemp chain thing to fix it. Even though it wasn't a counterexample, you still could color it with 4 colors or less, but it was a counterexample to his proof text. And he read the paper and he agreed that this was definitely a mistake. He even reported himself to the London Mathematical Society and said that this was a major error. And so both of them obviously still thought it was true, everyone still thought it was true, but neither of those 2 people were ever able to fix the error. Actually, Haywood dedicated his life to trying to solve it and was never able to. But it was a really important piece of the puzzle though, these Kemp chains. So in part of this proof, he used these Kemp chains to show that every map contains a region surrounded by 5 or fewer regions. And so if there's a minimum counterexample, it had to be when all regions were surrounded by, were surrounded by 5 or fewer regions. So they kind of knew what it looked like if there was a counterexample. So he verified the case when it was surrounded by exactly 5 regions, and so in order to prove it, they just had to show this very special case, right? So his proof led to the smaller case, which kind of led to a smaller case, and then other mathematicians were able to prove smaller things, right, that there were some certain unavoidable things that you had to have, and at that point they just put it into a computer and were just exhaustively checking these cases just to show that they could all still be colored with 4 colors. And so that is really, how it was proved with the heavy aid of computers. It was proved in 1976 by Kenneth Apple and Wolfgang Haken of the University of Illinois. And the fun fact, one of the people I work with at YSU was actually at the University of Illinois as a student when they proved this, right? So he likes to tell me that story. So it results in it actually being a theorem, right? That definitely, if you give me any planar graph, we can always color it with 4 or fewer colors, so that every 2 adjacent vertices are colored differently. All right, so yeah, so it took 124 years to prove it. And since it has this kind of heavy aid of computers, and I think the proof is like ridiculously long, right? No, not everyone has even read the whole thing. There's a little bit of doubt. I think we all believe that it is true, but I think there's still a little bit of a call for some sort of more theoretical proof somewhere, right? So, all right, so that's the quote from the beginning. And so now hopefully it makes more sense. So Wolfgang Haken were the people who proved the four-color problem, and so Smoke the Kraken, which is the four-color problem, 1, 2, 3, 4, the monster's no more. So I like that. That's kind of a fun little quote. Okay, so this is a super popular problem, right? And so a lot of cool mathematics was developed in trying to solve it, and also like through this whole process, it kind of brought graph theory to the limelight that it, is really kind of interesting and important. And even within graph theory, coloring became a really popular subject. There's a lot of real-life problems that actually you can solve with graph colorings. I won't go into them, but I'll list them for you. So scheduling problems, packing problems, communication problems, all of those have kind of a solution within graph colorings. All right, so we're going to switch directions a little bit. So a lot of mathematicians have studied these as they apply to other things, right? So not just purely graph colorings. So I'm going to kind of look at a combination of graph colorings and then something else. And it's related to another really famous conjecture in graph theory, actually. And this one has never been solved, so. All right, so we need a couple more terms. So a complete graph is just a graph, so a complete graph on n vertices, we label it as Kn. It just means that every vertex is connected to everything else. So if we have 3 vertices, we have a K3, which is just a triangle, K4 and K5, and so on, right? Just everything connected to everything else. And decompositions play a little bit of an important role in this topic. So we can take the complete graph on 5 vertices and decompose it into 2 triangles, the blue and the green, and then a 4th cycle, which is the red guy. And decomposing is just meaning that we're going to partition the edges, right? So every edge is going to end up into one of these graphs and only one of these graphs. All right. And another decomposition of K5 is into 2 C5s. All right, so trees are really important in this topic. So a tree is just a graph that doesn't have a cycle, right? So here's the star that you saw before, that's a tree. And then here's another tree that has no cycles. And so obviously these guys are not trees because they have a cycle, right? This is actually a cycle, and this guy has this triangle here, so he's no good. All right, so another conjecture that we're going to talk about is due to Ringel and Kotzig. So it's a little bit wordy, but they conjectured that if you take any tree that has m edges and you look at the complete graph on 2m plus 1 vertices, that you can decompose it into those trees, right, that are all isomorphic to T. Okay? So a really important player, Rosa, is one of Kotzig's students, and so there's a whole line of problems here that started with the Kirkman schoolgirl problem, which happened around the same time as the four-color problem started in the 1800s, and led to a bunch of things, which in turn led to this thing called graph labelings. All right, so Rosa attended this conference in Rome, and he gave this talk on valuations of graphs, okay? And one specific valuation he came up with what he called a beta valuation. Okay? And so he proved that if a tree has this thing called a beta valuation, then it satisfies Ringel and Kotzig's conjecture that we can decompose this complete graph into those trees. Okay? So beta valuation is not a super fun name. So when he gave this talk, it didn't really blow up because nobody really liked this name. In 1972, Golem did the whole thing and they relabeled it as Graceful labeling instead of calling it a beta valuation, and that's the name that stuck because it's kind of just super fun and catchy. So if you're coming up with your own thing, make sure it has a catchy name. So now this is a really huge area of study because partly because I think that this name is catchy. And now there's whole things like, there's graceful labelings and then harmonious labelings and all sorts of things like that. So people have gone on, and elegant labelings, there's all these different ones that people just have gone on because of that. So let me tell you what a graceful labeling / beta valuation actually is. So if you have a graph on n vertices and m edges, I'll do this complicated version and then I'll tell you what it really means. So you have a vertex labeling using the colors or labels, I guess, 0 through m, right? M is the number of edges. You want that to be 1 to 1, and then you're going to induce an edge labeling using the labels 1 to m, by just subtracting. So for an edge, you just subtract the labels of its incident vertices and make it positive. And you want those both to be 1 to 1. So what this is really saying is that you have these colors 0 through M on your vertices, and no two vertices are going to have the same color, right? That's just the 1 to 1 part. And then you induce it with this thing, you just subtract, and then the edges also are going to all be distinct, right? And since you have exactly the labels 1 through M, and you have M edges, then you have to have every label exactly once, right? So a pretty hard thing to have. And so if something has a graceful labeling, we just call it for graceful graph. All right, so here's an example because I think that definition makes it sound harder than it is. So all you do, right, so we have this graph of 4 vertices, 5 edges. So again, on the vertices, we can use 0 through 5. And we can't use something twice. And then if we look at any edge, we just get its label by subtracting these two, right? Finding the positive difference of those two labels. And then if we get exactly the numbers 1 through 5, then it's a graceful labeling. So this guy is a graceful graph. And the main problem is just determining which graphs are graceful and which aren't. So here's 2 more examples. So we have this triangle is a graceful with this labeling. This cycle C4 is graceful with that labeling. Every graph of order 5 is graceful except for these 3. So if something is not graceful, like these 3 guys here, there is a concept that we can kind of use to measure how graceful is it, like how close is it to being graceful. So if we look at the smallest integer k, such that if we use the numbers instead 1 through k instead of just 1 through m, that we get, this distinct vertex labeling, distinct edge labeling with the induced stuff being the same, right? So how far above m do we need? How many more labels do we need? So that number is called the gracefulness number. And this is obviously only going to be m if and only if it's graceful. So we have some bounds for this gracefulness number. So obviously it's bounded below by the number of edges, m, and then just kind of greedily it's bounded above by 2 to the n minus 1, because you could just label all the vertices with powers of 2, and that will always work. All right, so some results. This is a really popular area, so there's pages and pages of results on this, but some well-known ones are that cycles are graceful if and only if their orders are 0 or 3 mod 4. Complete graphs are only graceful if the order is less than 4. Every tree with at most 4 end vertices is graceful. Every tree of order at most 27 is graceful, but almost all graphs are not graceful. So this almost all graphs are not graceful just means, like, if you look at the ratio of graphs of order n that are graceful, graphs of order n, and you take that limit as that order goes to infinity, it's going to tend to 0. Oh, yeah.
So if you get a tree of order 28, what happens?
Oh, the tree of order. So there is a conjecture, I'll get to it in a second, right? We think that it will be graceful, but I don't know, they haven't proved every tree of order 28 is graceful. Yeah, but we think it is. It should be. And there's certain subclasses that they've proved are graceful. Like I think all caterpillars are determined and things like this, and all paths and whatever. But just if you give me any old random tree, it's not known whether or not it's graceful, maybe. Yeah. But yeah, the conjecture is that every tree is graceful. Yeah. So they are working towards trying to prove this thing. And this again comes from the Ringel-Koetzig conjecture, right? Because Ringel and Koetzig conjectured that, every tree, you can decompose the complete graph on whatever vertices into all these trees. And then Rosa proved, okay, you can do it if it has this graceful labeling. So of course they're going to conjecture, well, I bet every tree has this graceful labeling, right? Because they're basically just conjecturing that their own conjecture is true. But this has not been proven, right? A lot of people have been working on this, which is why there's so many weird cases of trees that have been proven, but nobody's proved it, that every tree is graceful. All right. So this is a well-known fact about decomposing. So one of the big reasons that Graceful was looked at in the first place was because you know how to decompose things into that type of graph if it's graceful. So if you have any graph G of size m that is that's graceful, then you can decompose the complete graph on 2m plus 1 vertices into copies of that graph. Right? So Rosa's original theorem was just trees, but we can actually do this for any graph. So I'll do an example for you. So if we take the triangle, right, we know that it's graceful. This is its graceful labeling. And we're going to decompose then the complete graph on, again, 2m plus 1 vertices, so 2 times 3 plus 1, so 7. And here's how we're going to do it. It's actually really cool. You can cyclically do this. So if we take this triangle with its labeling and we put it exactly in K7 in a specific way, so we label the vertices of K7 like that, And then we put it in there corresponding to its graceful labeling, right? So it had vertices 0, 1, and 3, so we're going to put it at 0, 1, and 3. And so now this edge that is labeled 1 from the graceful labeling just connects 2 vertices that are distance 1 on the outside cycle, right? And now this edge 2, right, connects 2 vertices that are distance 2 on the outside cycle, and this guy connects 2 vertices that are distance 3 on the outside cycle. And so if you take that and you just rotate him, right, every time you rotate him, this guy's picking up the edges that connect vertices of distance 1 on the outside cycle, this is distance 2, that's distance 3, that's all the edges in the graph, right? So if you do this a bunch of times, we're going to get exactly that decomposition. So our original one is here, right, and then the next one, is there. So we can do that all the way around. So the greenish ones are all the distance 3 on the outside cycle, and then the purple is distance 2, and the red is distance 1. That's all the guys. So you can do that, with any graceful graph of size m for any complete graph of order 2m plus 1. You can do this cyclically. Yeah, so we're going to look at this kind of combining the graceful labeling into a variation that involves colorings. So just regular old graceful labelings can be thought of as graph colorings if we think about rainbow colorings, right? So rainbow vertex coloring is just what you think it is. It just means that every vertex has its own color, right? So no vertices share the same color. And so if you think about the graceful labeling, right, all we required was that all the vertices had a distinct label, and then the induced edge labelings were all distinct. So it's really just requiring that we have a rainbow vertex labeling that induces a rainbow edge labeling, right? Or coloring, right? Using this kind of induced thing, right? So that's the traditional one, right? But as we know, the most kind of popular types of colorings are the proper colorings. And so the problem that I looked at when I was in grad school and working on my dissertation was instead of doing rainbow inducing rainbow, we're just doing proper inducing proper. So we're going to call this a graceful coloring versus graceful labeling. So a graceful K coloring is really the same thing, right? The only difference is that we have a proper vertex coloring using these colors 1 through K, inducing a proper edge coloring using the labels 1 through K minus 1 or colors 1 through K minus 1, and then we just define again the label of an edge is the difference of its incident vertices. So just the same thing, proper vertex coloring inducing proper edge coloring. And so, yeah, a graceful vertex coloring is a graceful coloring if it's a graceful K coloring. All right, so here's the cube, Q3. So on the left here is a 6 coloring, so we'll just use this to demonstrate like what is going on here, right? So on the vertices, I'm just coloring 1 through 6. And I can have some vertices have the same labels, the same color, right? It's just as long as they're not adjacent, that's okay. And then we're going to induce the labeling on the edge the same way, so it's 2 because that's 6 minus 4. And again, we have like 3 2s going on here, but they're just not adjacent to each other, so that's okay. Of course, we can do a little bit better, which is the whole point of this, right? Same with like proper colorings. We always want to look for the minimum number of colors we need. So if we can do better, that's good. So for this guy, we can actually get away with 5 colors. So in general, we want to know what the minimum number of colors that we need for it to have a graceful K coloring. And so we call that the graceful chromatic number, and it's this little chi-CG. All right, so some graphs that we've seen before. So K4 has this graceful 5 coloring. Here's a graceful 4 coloring of C4. So the thing to notice is that this gracefulness and the graceful chromatic number can be different, or they could be the same. So for K4, this is actually strictly less than its gracefulness number, but this one is exactly the same as its gracefulness number. So we get some bounds here, just based on the stuff we know about graceful labelings and chromatic number. So if we have any connected graph of order at least 3, then definitely we're bounded above kind of by the gracefulness number, right? Because if we have a graceful labeling, that's going to work for graceful coloring. The reason we have this +1 is because, I guess maybe a little oversight when we were defining it. If you notice, we started at 1 here instead of at 0. Whereas graceful labeling started at 0. So we have to have that +1 because if you have that graceful labeling, you might have to shift things up by 1 if you have a vertex labeled 0, right? So there is this +1 here. And then obviously it's bounded below by these bounds on the proper colorings because if you can't properly vertex color or properly edge color with that many colors, you're never going to be able to get a graceful coloring. Yeah, and since the chromatic index we know is either delta or delta plus 1, then we have this bound, a lower bound for the Graceful chromatic number of delta plus 1. And that is achievable if you think about a star. We need delta plus 1 colors, right? Because this guy is adjacent to all the other guys, so he'll have a color, and then all of these guys have to be different than him, right? And they have to be different than each other, because if these two were the same, then those two edge labels would be the same. It wouldn't work. All right, so another observation is just if you have a subgraph of your original graph G, then its Graceful chromatic number is less than or equal to it, right? Because the Graceful coloring of G is going to work for H. All right, so this was a useful observation and an alternate definition of Graceful colorings. It was helpful in some of the proofs that we did, but I think it's just kind of interesting. So if you just have a vertex coloring using the colors 1 through K, then it turns out it's a Graceful coloring if and only if these two pieces hold. So the first piece is that if you look at every single vertex in the graph and all of the vertices in its closed neighborhood. So closed neighborhood just means everybody it's adjacent to and itself. So if all those guys are distinct, that's our first condition, right? And that's just guaranteeing that we have a proper vertex coloring, right? So like for this guy, we need him to be a different color and all of its neighbors to be a different color. The second piece is just that if you look at any path of order 3, then the middle guy can't have the same color as the average of these two colors. And that's guaranteeing that there's a proper edge coloring, right? So if these two are odd, so it's never gonna work, right? But if we added this guy and that guy and divided by 2, then these two edges would end up being the same color, right? If that was the same value as the color of B. So some results that we have, we found the Graceful chromatic number of all cycles. Oh, and I'll make a comment, right, that every graph has a Graceful coloring of some sort, right? Because we proved that bound that it's always less than or equal to the Graceful number plus 1. So this exists for everything. So there's no conjectures or anything that like, oh, these things have this Graceful coloring. It's true for everything. It's just a matter of finding it. So for all cycles, we have found that they're all 5, essentially, unless you're looking at C5. And really the reason that C5, you need 5 colors is there's kind of a lemma in there somewhere that if the diameter is 2, so if you can get from any vertex to any other vertex in 2 steps, you need all the colors. You need a different color for every vertex. And so that's what's going on here. And then for C7, this coloring will work. We pretty much just found colorings for all the other cycles, I think depending on what their order was mod 4. And then due to the cycle result, since we have this kind of observation about subgraphs, since paths are subgraphs of cycles, we know what the Graceful chromatic number of all paths are. We could prove that it's always 4 as long as you're looking at least P4. All right, so we also looked at trees. Obviously, there's this famous Graceful tree conjecture, so we had to look at trees. So one really popular tree, and this is going to be like the weirdest sentence if somebody's walking by for me to say, but a caterpillar is a tree if you remove all of the leaves and you're left with a path, right? So if you take a tree, you take all of its leaves off, and you have a spine, then it's a caterpillar. It makes no sense. But this is the words that we use. So here's 2 examples of caterpillars, right? So if we remove all of those guys, we're left with that red thing, which is like the spine. And if we remove all of those guys, we're left with that red thing. So we're able to prove definitively what it is for all caterpillars. So essentially, it's always going to be maximum degree plus 1 or maximum degree plus 2. It's only going to reach this bound if you kind of have this situation of all the high degree stuff being clustered together. So if you have a vertex of maximum degree adjacent to 2 other vertices of maximum degree, then you need another color. You're going to need that delta plus 2. But in all other cases, you'll need delta plus 1. All right, so trees were a big topic that we had to look at because of this Graceful tree conjecture. So, so just in the caterpillar case, we saw trees where we had the Graceful chromatic number be delta plus 1, somewhere it was delta plus 2, and so it led us kind of to ask the question, is there, a tree where the maximum degree and the Graceful chromatic number is greater than 2, or is there a constant, right? Can we bound this some way? So to answer this, we have an example that proves that that's not true. And you can find more examples to make this number be more things, but so there really isn't a constant that we can kind of bound this above by, like delta plus something, but we have a bound in a second that I'll show you. So the reason this ends up being kind of bad in a way that we need more colors, we need more than delta plus 2 colors, is because you'll notice we have a lot of maximum maximum degree vertices adjacent to each other, right? This guy's got degree 4, so does that guy, that guy, that guy, that guy, and they're all adjacent to that guy. So you need more colors for this guy. But, as I'm sure everyone has noticed, 7 is really the ceiling of 5 delta over 3, right? Obviously. So because of this one and a bunch more examples that we saw, this number kind of kept creeping up, and then we kind of thought of a rationale for why this number is creeping up. And so this proves an upper bound for all of these results. So we're able to prove that if you have any tree with maximum degree delta, then this is an upper bound for the Graceful chromatic number. And it's sharp, right? Just meaning like we can't do any better because obviously the graph we just saw achieved this. So there's no better result. But that's as good as we can get on trees. We don't have some distinctive number. And that is about all that I'm going to share with you. There's more results. There's papers out there you can read if you want to. But there's still a lot of open questions, right? So there's a lot of other kind of variations of labelings you can do this thing with, right? You can do this kind of, applying a proper coloring instead of a rainbow coloring or something of that sort. I'm even going to try to do something with this topic in the spring with some students, and in the summer I have another project that's related to this. So this is a really good area if you want to try to find some research topics. So I'm working on this with some undergrads and grad students currently. So first I want to thank everybody for coming, and then I want to thank Wittenberg for being so supportive. Here's a bunch more embarrassing pictures that you can look at that I found and stole from some people. So yeah, Wittenberg was such a great place, and this is at Dr. Parker's house for a Christmas party. That was our certificates. That was at Al's house. Is this at Al's house?
Yeah, that's a Putnam.
Yeah, that was the Putnam, right? This is just me and Vicki because we made this poster, which is no longer hanging up out there, but it was before. We came back for homecoming. That was that was one of the MAA meetings. We had the flag thing for some reason, so I don't know. And then that was me graduating with the job, same people in here, just Dr. Higgins now, Dr. Shelmer, Dr. Parker. Oh, Flavia's there. Yeah. So, anyway, so thank you. That's all.